Okay, guys, so now we're going to try to look at the power of pharmacodynamics. So if we model both the pharmacokinetics and the pharmacodynamics together, remember the issue to begin with is that what we really want to know is what our dosing regimen needs to be to get a particular effect, right? So we want to know what do we need to give, what our dosing regimen needs to be to give a drug to get a particular effect. That's what we're really looking at. But what we know is we can use pharmacokinetics. I'm going to change colors. Okay, we can use pharmacokinetics to link the dosing regimen to blood concentration, right? So kinetics tells us the concentrations of drug we get in the body for when we give a particular dosing regimen. But we also need to get from concentration to effect, don't we? Why is this happening? So in order to do that, we need the other part of the puzzle, which is going from concentration to effect, which is pharmacodynamics. So if we add the pharmacokinetics and the pharmacodynamics together, we can go from a dosing regimen to an effect. And this is super exciting stuff, in my opinion. So, and I think that it's possibly something that you will see used in your practice in your lifetime, more than it is now. It's not used that much now, but it will be. So from now on, for phase 3 and 4 trials, we use modeling a lot to determine the best dosing regimens. So when you apply for a new drug application, NDA, a new drug application, the NDA, the FDA wants not only the clearance, volume, bioavailability, which are all kinetic terms, right? Kinetics, they need that. But they also want Emax, C50, and gamma. And these are all dynamics, right? So they not only want to know the kinetics, but the dynamics of the drug. So if you have, for an example, a new drug given by IV infusion to a patient or other healthy volunteer for some period of time, and then blood is drawn for both pharmacokinetic parameters, so they get the blood for the concentration so that they can do a concentration time curve. Well, I guess if it's IV, it's going to look like this, isn't it? Concentration time curve, but they're also going to be, during these time periods, they're also going to measure the effect and response for the dynamics so that they can relate concentration to effect. So they take these concentrations from here and then they've measured effect so that they have some kind of relationship with the effect. So they do both the pharmacodynamics and the pharmacokinetics. Now, so what we can do is we can put these two models together. As you know, to determine a concentration at any time during a constant infusion, you take your dose rate, or your KO, or whatever you want to, people name it, all different things, RO, the rate of drug that you're giving, so your infusion rate, or what I've been calling dose rate, over clearance, times 1 minus e to the negative kt, this t being whatever time you want to know during that infusion. So that's time t, wherever it is along here. So if you want to know that concentration at time t, you just have to put that time in there, and you're going to put in your dose rate, your clearance, and if you know the k, you can determine your concentration at any time t along here. If you stop that infusion, I'm going to just write that out a little clearer. So here we start an infusion and we give it at any time t here, we can determine it. If you stop that infusion here and then the drug starts to decline, this is concentration, this is time, then you can determine after the IV infusion here at any time t using this equation, right, where we put the t in here. Well, this is still representing this. So this is that same equation. If you give it, let's say you give it for 2 hours, so you put 2 hours here and you want to know 2 hours after that, or let's say 3 hours after that, you put 3 in there, right? This is just simple one compartment kinetics that you learned earlier in the semester. If you use that and you use your Emax model, right? So let's say that we know that the kinetics follow, or the dynamics follow the Emax model, then we can just put this concentration in here if we know the C50 and the Emax. And that's what this next page is going to show us. We're just going to substitute those in there. So here's our, whoops. So here's our Emax model, right? E is equal to Emax times C. We got this C from our concentration during infusion, right? So we're giving a constant infusion. We want to know this concentration at time t. We put that constant, that's how we figure that concentration in there, right? And then if we know our C50 and Emax, at any particular dose rate, at any particular time, we can figure out what the effect is going to be. Pretty cool, right? It's using these two models together. This is the same thing, only we've put the equation in for the concentration after stopping the infusion here. We can do this for anything, right? This is super powerful because we can solve for what dose rate we need to get a certain effect at any particular time. Super cool. Okay, next we're going to talk about the temporal aspects of the effect models. So we'll see